продолжаем наше погружение в формальную верификацию смарт-контрактов в Ethereum.
We delve more into formal verification of smart contracts in Ethereum, in positive technologies, in Web3 security. I'm also studying in Moscow State University. I study formal verification. I was involved in the blockchain project, and I'm the author of a few articles, and I tried to do this course of mine on formal verification of the Isabel. Like Sergey said in the previous presentation, formal verification is the mathematical proof of our program actually meets the current specification properties. In my presentation, we try to embrace this field much more, so I'm not stopping here at the formal verification. I'm considering all type of approach, and I would like to speak about how we can use formal methods. You may agree that the number of bugs overall in this field is growing. It's not because that we started writing the code worse. There is more code, and new projects emerge, new hackers appear who try to attack, automatic bots spring up that try to use vulnerabilities of the projects deployed. And overall, the code of the smart contract cannot be changed after being deployed. There are some proxy patterns and other methods to change the code by address, but you cannot always do that. You should say that we have this testing and audit which will help us find mistakes, but formal verification is different. It cannot only find the existing errors, but it helps prevent their absence with the absence of the formal methods. And apart from that, in terms of audit, the auditors are the same people who find the same mistakes. They try to use the automated tools, formal methods. But they are the people, and people tend to make mistakes. They are not computers. Yet formal methods are not with people. It's the engineers like us that do that. But with formal verification, we just put on a logical core, some axiomas. We do not put our trust on human. We just prove theoretical theorems. Theory. With formal verification, we conduct an audit. So here is the stage of specification of properties. We realize what would be the properties of the contract that may be performed and which may not be. And so I've given you the quote of one of the famous computer scientists about testing, that the testing, but it may not prevent its absence. Sergey has also provided that, first of all, we just take the source code, then we write the formal specification, which should be fulfilled, and number three, it's the formal proof, which we conduct either by hand or on paper. But it's not going to be that convenient, or interactive proof, or with the SMT resolver, or the computer may find a counter example. Like, for example, in the first method on this graph, we have model checking. When we see the model as the transition, then we launch the model checker. Preliminarily, we put the temporal logic-based description. Then we launch the computer, which goes through all of these states and finds out whether the properties are fulfilled or not. Then, if not, the counter example follows. If it's fulfilled, then it would stop on a certain boundary and would say that the properties are intact. There are some interactive proof, probably Sartora. is there. It's not just like model checking, just because the language in which the model checking model is simple enough. We have arithmetic, we have simple logic, and the complicated model will not be based there. The automatic proof environment uses meta languages like OCaml, the ML standard. These are the meta languages, as they're called, because you can describe other languages using them. And they are powerful enough as compared to the model checker languages. And due to that, you can be creative enough, and there will be less automation there. And the third stage of the proof creation, it could be automated through resolvers, but it could be less automated when we use tactics for proof. Tactics is the function which transfers term into some other terms or a list of terms. So the verifier, the user, provides the continuous set of these checkers, and they are all verified. Let's just move to the instruments for Solidity. I stopped at Solidity because it seems like Solidity is most popular language for smart contracts, but the approach I describe can be applicable to other ecosystems, but it's a separate topic to discuss. And the first tool that stands out here is Solidity SMC checker, or Solidity SMT checker. Is a simple model checker which is embedded into Solk compiler. It started in 2019 and it was developed by Ethereum Foundation. They made a publication about that. So Sol SMC actually you first Solk, you call Solk with a syntax tree, an abstract one, then it transfers into the first stage formula, which is called constrained horn clauses.
Затем их выполнимость проверяется с помощью SMT-решателей.
They are all verified with the SMT resolvers. But the question is, how do we specify the properties? The properties are specified in the code with assert and require. We cannot specify all of the qualities anyway. We'll go back to that, but immediately I should say that we can write a special function with a contract, and then we put assert, and see how the variables can be checked. So we'll compare Sol SMC with other instruments later on. Moving on, outside of Sol SMC, there will be other tools which are not related to Ethereum Foundation, some other frameworks, and two main types of approach should be singled out here. First of all, EVM bytecode verification, where we verify the bytecode which was generated by the compiler. So what do we need here? First of all, we need some semantics of Ethereum virtual machine. We need to build a certain stack model and find it through yellow paper. And we need to have a parser for bytecode, which will transfer it to drop codes. And then we formally verify it, but then we need to think about how we can verify the properties. And the second approach is the verification of the Solidity source code. For this, we need to translate the source code, not the bytecode, but the source code of Solidity, where we will prove this theory. Then we just need to simulate the smart contract realization. And a few spoilers here. The verified Solidity translation does not exist in the Solidity environment.
Для этого нам нужно придумать инструмент кода
For this, we'll need to create the code generation tool from where we will generate something very similar to Solidity, and we'll compare it with the initial Solidity semantics. We'll discuss such things later on.
Преимуществом первого подхода, вернемся к ним.
We'll
То есть,
go
как я
back to
сказал,
the
здесь мы верифицируем как бы
advantages.
да, хоть и байт-код.
Here we verify the real bytecode. It's a real bytecode, which we have here in the net.
Из недостатков здесь это спецификация свойств. Да, непонятно,
But
как
there are some disadvantages, which is specification of properties.
это, по сути, никак не
How do we specify the properties
просто парсер,
in this case? Because we only have the parser for the bytecodes and the formalized approach. So here the properties
не очень. Вот. И как показывает практика, есть
do not go here easily. So here there may be a problem with the implementation
свойств
of the specification of properties of the function with the external call and the externally owned
и
accounts.
непосредственно к инструментам. Давайте перейдем.
Now we would like to say a few words about instruments.
Я выделил не все, но самые
I singled out some of them, the basic ones. The first one is the tool, the type of the research is the EVM in LAM tool, which starts in 2017 when Yoichi Hirabi in GitHub decided to put a list on how they see the formal verification of smart contracts in Ethereum, and he became a creator of this verification of the bytecode, the Solidity. So he described the entire path, the entire work. He made LEM. LEM is a meta language which is used to describe other languages, and he explained why he chose that. LEM translate well into Coca Isabel, and he chose Isabel out of it. So he realized the EVM semantics, and he translated that in EVM, started generating the proof. It didn't work out well, but he could prove some simple properties of a contract re-entrancy, like for instance. But actually they dropped the project quite quickly. All the other contracts were based upon that experience. The KEVM of runtime verification, which is a well-known one, and it's developing further on. So, it's formal semantics EVM in K from work. So apart from that, from the EVM model, they have got a simplified network model. The high-level model, the ABI calls, they formalize the EVM on Haskell, which is called HEVM. It assumes automatic verification with the SMT resolver Z3. And the most appropriate tool here is Certora Prover. Sergey spoke about Certora Prover in detail in the previous presentation. Because of its interface, it's great, and its specification language. It's very good that we have the language of specification in which we can describe the properties. I'm not going to get deep into it because Sergey dedicated 40 minutes of his presentation to Certora Prover. Right now, there were the false negative and false positive results of the use of Certora Prover. 1.5 months ago, there was an FMBC, Formal Methods for Blockchain Conference 2024, and there was a benchmarking towards of Solidity verification tools. They compared Certora and Sol SMC as the most highly performing tools, and they took that and they audited simple contracts and they compared them with the results of Certora and Sol CMC, and started comparing that with Sol CMC and Certora, and they found false positive and false negative with completeness, reliability, and expression. So we know that if the property is complete, whether Sartora and Sol CMC can prove it. Reliability is the most important one. That's the second one. It relates to the false positive result when the condition is not met, but the tool says that it's complete and it can prove it. It's the bad thing. It's like when we use the tool, it seems like to be checked and verified everything, but it's not true and it led to a vulnerability. And then the expression, what we can describe basically, it relates to the liveness, that's what it's called. If there is a certain set of states, in any state, something good can happen and we can withdraw the money safely and nothing bad can happen. Oh, and we can't withdraw. So there are theorems like this. So Sartora, with its specification language, in terms of the expression, is much better than assert require.
Что касается полноты, то там основная проблема была с внешними вызовами тоже.
There was the main problem with external calls with false negative results. The false negatives would start with external calls, and Sartora didn't really know what kind of code hides there. It knew that the property is not fulfilled, and the external accounts things. For example, we have a withdrawal function in the contract, the withdrawal function, and we try to prove the global quality. If we call this function, the balance message sender balance increases, but formally it's not fulfilled. When there is a contract, we don't know what is going to happen to the balance after this call. If some address without the code is done, then the balance ideally need to grow. The first property does not change. We can write it, but it's not going to be proven. But the second property will be proven, but we can't describe it. So there are such limitations that arise. If there is a limitation, it would be logical to move to the second approach. I guess the second approach will save us from these limitations. And this is the approach which is about verification of the solidity source code, verification with some deductive methods. We use interactive methods of proof, Coco or Isabel. They speak their own meta language, which can be used to specify almost all of the properties so that we can prove them. But the disadvantage of that from solidity to these meta languages are not enough, but transferring them there does not make us trust. So we can create some plugins for compilers, and there are some results, but for solidity, such things do not exist. Right now, let's just move to the tools. There are plenty of them with some deductive verification. I just selected 3 of them. Let's just discuss one of them more in detail. I'll try to demonstrate, make a demonstration here, how we use it to find the vulnerabilities. And the first one is Isabel/Solidity, an interesting project which is rapidly developing. It's the deep input of Solidity into Isabel. The deep input, the 2 types of the input of the language into meta language, the deep and shallow embedding, it's called. So if we're talking about shallow embedding, we try to use the existing constructions of meta language to describe the properties of the target language. And the deep embedding is when we create inductive types, the new types, and they help us do the deep embedding. So the solidity, Isabel solidity, is exactly about that. To test that embedding, we just need to test the semantics of solidity with real semantics, and that framework is also realized there. We just formalized reentrance in there in Isabel/Solidity, but this semantics does not look complain of Isabel Solidity, but this project is growing and can be used as a very good tool. The only global problem, as we see it here, is that we run in the different direction. There is no connection of it with the source code of Solidity. Not all can write using Isabel, but everyone uses Solidity. The cock of Solidity tool is no longer developing, but here is a very interesting idea. The creators of this tool have a very interesting project. Startup is entitled Formal Land, is that they completely translate the target language to cock, to the proof environment. It's a very difficult task to perform, but they take abstract syntax tree of Solidity and try to translate this abstract syntax tree. Somehow they stopped this project. Actually, at the phase that when we take a contract, we can announce the state variables, write some simple functions with conditions, operators, nothing that, and we translate that. It's an interesting idea, but as we can see, the developer is actually encountering quite a number of problems. It is time-consuming and money-consuming, labor-consuming. But the most interesting and productive tool, as we can see it here, although the new ones, is Concert. Concert is the framework which combines smart contracts of the execution environment and the test features and code generations. You can use this not only for Solidity, but you can generate safe contracts to other target languages. So what about this cock and Isabel? These are words that are unknown for many people, but cock is the environment of interactive proof of theoremas. It's the set of tactics which are verified and checked, and it has a number of axiomas. And the meta language which is used is there to verify. And there are three tools that are used here. The LIM, very often it's used in mathematics and Isabel and cock. Isabel and cock are very often used to verify the real software. But we stopped at Concert as the most developed instrument, and it's based upon cock. So I'll speak about cock. The meta language is used here is Galena, the functional language. It's like other languages, has the type of theorema. So it's a couple of a theorema and a setup of tactics that transfer these terms. A set of tactics is the proof of the theorema. They are checked and verified, and this set of tactics is written in cock. A cock has tactics, and it has a separate language which is called meta-cock. Now we'll see in the example of Concert why we need this. For code generation, on the right-hand side, let's just check this out. From Concert, with this meta-cock, we can get the verified code of smart contracts and 4 languages. The 4 languages are very seldom used languages. And Rust. Well, with Rust, there seems to be a problem. But we can translate it there as well, and there is no release of it yet. But we keep it, and we are interested about the left-hand side. That's what we use for formal verification of Solidity contracts. Manually, we rewrite the smart contract in Coq by using concert. It also has a model of the environment. It also has the property-based testing, and Coq has a quick check. I'm not going to speak about that, but concert has lots of articles to read, and with this concert framework, a lot of vulnerabilities were found, and some of them was even prevented. So this tool is used and utilized quite successfully. Let's just drill down a little bit more. What about the representation of the smart contract? In concert, there are two functions, init and receive. You can see them there on the right-hand side in the picture. Init is used to construct. It's a constructor based on solidity. It's to initialize, to deploy the contract with the current state of variables and receive. We wrap all the other functions into it. It's one function for all the other ones. Chain is the overall information about blockchain, the block number. So the context of the call are the parameters, or rather, who we receive this transaction from. Setup and message both contain these call parameters, and in the output we somehow need to update the state. So list action body is the list of the transaction. That's what smart contract is represented there. But what about the environment? We know that there is the execution environment. All the blockchain actually is the environment. So we have this information about blockchain in the chain type, and there are two functions there made up of addresses, like, for example, V-contract, E-contract to represent the contracts. Maybe you're familiar with functional programming. Functional programming has the type of function none or some. None or some. If there is nothing there, there is none in the output of this function. And if we have some, then we'll have a contract. A contract must be in some state. There is a state of the contract, and that's what these env contracts address claims. Option, weak contract. So here is the transaction which is modeled by the action. So from whom we've got this transaction, which is the origin and act body. And in order to evaluate how these action transactions affect this environment, action evaluation is used here, which is working with the previous state, then works with transaction, which is action, the new state, and the list of actions, the list of created transactions. Then it checks and verifies that such a set occurs. For example, the number of block increases by 1. By the number of 1. In order to identify the liveliness, that nothing bad happens, we need to have another trace model. Is a set of states. This trace, as we call it, is when the two neighboring states are chained, and they're chained with a chain step. We either add a block, or we fulfill the transaction, or we move the list of the transactions. So that's where you need to put in the concert. Manually, using Coq language, our smart contract must be rewritten, taking into account all of the smart logic, and it should be verified. And we tried to use concert for formal verification of the DEX protocol and the automatic market maker, AMM. From a hackathon, we borrowed that from a hackathon, last year, which one of the smart contracts. When we create a couple here, pair here, we can set a commission fee, an inadequate commission fee. Nobody would ever exchange this with this commission fee. And I'm showing this screenshot to you on purpose because now we will see how it looks in concert. We take this contract and it has 5 functions, standard functions. We create a pool, we top up the pool, withdraw from the pool, withdraw the commission, and we do the exchange. And here's a wrap-up cover message. This cover message is put into receive, and receive knows by this cover which function we need to refer to. So here's the concert wrap up. These are the entry points. This is what they look like in concert, expressed in Galena language that our COC speaks. Now let's just take into account the simple solidity code. There is no verification for commission fee, so we bear it in mind for the time being. It's a standard code, and why am I showing it here? I'm showing it here just to compare what it may look like in concert and in COC. And this is what it looks like. The function is defined by definition, the keyword. There are 4 parameters, the state parameter, and the monadic function occurs, either the new state or error. That's what it ends up with. So this is how it's rewritten in concert, by the way. As for mapping, there is a fmap library, so it's all done through fmap. And there is also pattern matching, as it's done in formal programming. Now we have the updated list of pull-offs with the ID, which is increased by the number of 1, and we have the updated map pool. Or error if somehow we do not pass this. So what would be the proof of theoremas? We can only prove the theorem of safety correctly. So it's made up of 3 points. First of all, we correctly update the variable of state. We correctly create new transactions when created, when there are no new calls. And it's all about this function successfully working only when we have proper parameters, proper input parameters. So the first theorema that expresses the first property of the correct update of the state variables. This is what it looks like. Definition is a predicate that we have certain inbound parameters. If everything is good, these parameters are updated like they should be. And it's a theorem for any entry parameter. If there is received with a create pair with such and such parameters, and if the transaction runs smoothly, this predicate equals 1. So the credit pair will be updated successfully. Then it's followed by the proof, after which we enlist track tactics, and it's finished by QED. Nobody will, of course, understand this syntax for the rest 15 minutes that we have here, but this is approximately the syntax that we need to study. There are books to read about COC. They could be tactics like control simple and fmap simple. It's a part of the concert. It was done by the developers, and all of the other tactics are used only in COC. So contract checker verifies this. So the term, as we apply this tactics, equals true, equals 1. Seems like everything works correctly. We rely upon computing, and about mapping, Sergey didn't point it out, but he said that Certora doesn't specify mappings, but it's a very important property. Like, for example, we have token 20, and we would like to verify the properties. If we did not mint the new one, if we did not burn the old one, the mapping is the sum of balances, and it should be invariant. It should not be changing because the tokens do not go anywhere. In Sertor, we cannot prove this, but here in Concert, we can easily prove this. But for this, we need this specification, trust specification. We need to write that in any state, the balance amount will not change. And it's easily proved by EBT, and you can prove it easily. We tried to verify this contract, and we tried to prove that if the user has put its funds in there, they will withdraw something. They will withdraw something. We tried to use this theorem, but everything broke because of this fee function. There's no verification here. And we can see unit amount minus fee may be less than zero, because sometimes the fee may be much bigger than the amount, then uint will be less than zero. It's not a vulnerability, but the revert will occur. There will be no overflow. But the problem is that violent users may just simply spam our protocol with the non-valid pools, and there is no such inspection. But in COC, we found it. As we were proving the theorem on correctness of properties, it was said that amount minus fee is less than zero. In COC, it's not possible. So overflow of the natural numbers could not help us prove the theorem. So we did not quite prove the global theorem on it working properly, which is sad. But formal verification really worked like it should. We proved something, but we couldn't prove it somewhere. So it seems like there is something wrong with the source code. So here's how Concert works. I have a little bit of time left. I wanted to speak about the distant vote verification. Through Concert, it was done in a similar framework based upon whole. It's called Call for the interactive proof of theoremas environment, and it was possible to prove that that voting is achievable. This approach works well with other ecosystems as well. So I think, in summary, I would like to finish at a very good note. Both Sertor and Concert are actively growing, are rapidly growing, and can be used for different purposes in the industry, and can identify a high level of security of contracts. As they develop, the price of the formal verification will go down. Verification of the contracts will be as easy as testing, so the formal verification price will go down. The guarantee of the solidity will grow, and this deductive approach, which is about the proof of theoremas and the liveliness of the contracts, survivability, can be used there as well. Hyperfabric was used as well, was mentioned, but it does not use the deductive method. However, it can be used there, but it costs money, and there are not too many experts in that field. I chose the Ethereum-based example in my presentation. Here are my contacts, by the way. If you like to ask me some follow-up questions, please contact me. You can write us to our email and order an audit, order formal verification if you like. Now you can ask me questions. Thank you very much. Java card, it was certified. It's a C compiler. This project is called CompCert. It's the formal verifier for C. It's one of the part of the Software Foundations book. For Isabel, there are some materials on YouTube. I uploaded a few videos. There are some works from the authors and concrete semantics. It's also a book, but it's not enough, of course. But as far as syntax and semantics, it's good thing to learn. What are the competences required for the engineer for formal verification? I just answered this question. And for formal checking, try just to resolve the task of the verification of the model checking of the consensus protocol. It's a hard task, but the syntax for model checking is quite primitive, so any developer can easily learn it. Alice Willampert is the author of this tool, is the author of this language, a creator, a famous scientist. And he reads a video course where he explains it quite well how to verify consensus, Paxos on TLA+. And for Certora, they also have a course. I believe Sergey mentioned that as well. I did not use Certora myself that much. So basically, for all of these tools, there are books to read, and there must be some minimal knowledge on mathematics and logic, and of course the desire to learn. The question maybe from the floor about PDG. Did you answer? Did you ask this question from here? I cannot decipher this. It's encrypted. I cannot decrypt it. What does PDG stand for? Oh, it's not the question that goes to me. Now I understand. Now it's clear. If there are no more questions, you have a question.
Вопрос такой. Есть
I have a question. Do you have any limits, reasonable limits of the volume of the code that can be formally verified in terms of verifying a protocol, for instance? What are the volumes, what are the amounts, how much time does it take, and where is the limit of the amount of the code? As far as the costs go, you can ask other people by using my email, corporate email. The volume of the code, the amount of the code, of course there are some limitations. Like, for example, if there is proxy pattern used, it's very hard to verify. But it's in FMBC, which was a month and a half ago, the morphism of the contracts and the updates of the Padre sum, and they created the solution of how to do that. There are some limitations, and we just need to take a look at the code, of course, to verify that contract. We don't take into account the view function. They don't affect the state at all. So I guess there are 100 and 150 strings of code. In Concert, it took 300 strings of formalizing Concert and a few thousands of proving the theorem of safety. So it's a lot of work, in other words. So maybe it's 10 times more or 100 times more, a few orders more, a few fold more.
Предоставит хорошие гарантии надежности.
That it will give a good guarantee of
у нее хорошее будущее, потому что она может математически просто доказать, что все.
So we can mathematically prove that it works or prove that it doesn't work. That's exactly what is needed.
Микрофон еще у нас 5 минут есть, я отвечу.
We still have 5 minutes, so I will take a couple of more questions as well.
Какие есть способы доказать, что...
What are the ways to prove that this model really matches the code?
Какие есть способы,
Speak up, please.
что модель действительно соответствует коду?
Can we really prove that the model really matches the source code? There are ways. There's the reverse way of code generation. It's possible. But it's definitely the most vulnerable part of the Concert. We write this model manually in Coq, and
Можно либо
we are not certain. Either there is code generation and we run some tests.
да, то есть проверять.
Some testing is required. We just take the input data and check and verify. But the ideal future is when we have the translator, the verified translator. For some languages it works, especially for functional languages like KML. We can have the standard KML, and POP4 we can take these functions with theoremas, and we can formally verify the translators and verify them into a different language. It's the ideal future, but we'll just see what it's going to look like.
Ну да, ну либо делать плагины для компилятора,
So we're going to take these plugins for compilers, so we just do the verified translators, or we do the tests and make sure that this model matches the source code.
Можешь открыть таблицу, которая по статье 24 года?
По-моему,
Can you go back to the slides? No, we can't go back to the slides.
ну да, мы обсудим.
It was deactivated. Okay, I'll ask you later. Okay, thank you.